In this segment, we'll talk about how we can numerically differentiate discrete functions by using the divide difference methods. We will limit our discussion to the first derivative of these discrete functions. So let's suppose somebody is saying that, hey, y is a function of x. And what they are telling you is that, hey, they are giving you this function f only at discrete data points. So let's suppose somebody is giving you only x1, y1, x2, y2, and all the way up to xn, yn. And somebody says, hey, find dy by dx, an approximation of it, of course, at x equal to xi. How do we go about finding the first derivative of this function y, which is only given to us at discrete data points? So if I was going to, let's suppose, show a plot of y versus x, I will have these n data points given to me. And let's suppose if this data point here is x of I comma y of I. And that's what I'm interested in, finding the approximation of the slope at that particular point. So this point here then becomes x of I minus 1, y of I minus 1. And this point right here becomes x of I plus 1, comma y of I plus 1. So what that simply implies is that now we can use the divided difference methods to be able to find what the slope of the function at this particular point is, by maybe using this point right here or using this point here. So if we use this point and this point, then that's called backward divided difference method. So that will be the slope of this line. So that will be from the backward divided difference method, as we have talked about for the continuous functions. If we find the slope of this line, then that will be the slope as per the finite divided difference methods. And if we use this slope, where we're going to join a point which is on the left and on the right of the point at which we're interested in finding the slope, then that is the central divide difference scheme. Of course, you have to remember that if we're going to use the central divide difference scheme, that the spacing between this point and this point has to be the same as the spacing between this point and this point so far as the x value is concerned. So that's extremely important to remember. So if we talk about it, hey, what is the derivative of the function f, which is same as y, at x of I, we can say, hey, it is f of xi plus 1 minus f of xi divided by x of I plus 1 minus xi. Because keep in mind that y is f of x, so it doesn't really matter whether we can also put it as y of I plus 1 minus y of I divided by x of I plus minus x of I. So since we are using the point ahead in order to be able to find the value of the derivative of the function, this formula will then be the forward divide difference formula. Now similarly, if we want to look at the backward divide difference formula, that means that we are taking a point behind it, then in that case f prime of xi will be approximately equal to the value of the function here. So that is the same as saying that, hey, it is y of I minus the y at the value of x of I minus 1 divided by x of I minus x of I minus 1. So that is the backward divide difference formula. Now if we want to look at, hey, what is the central divide difference formula for the same thing, then it will be simply f prime of xi is approximately equal to the value of the function at x of I plus 1, and subtract from that the value of the function x of I minus 1. And then in that case, the run will be x of I plus 1 minus x of I minus 1. But here, what we have to make sure that when we are looking at the central divide difference scheme, we got to make sure that x of I plus 1 minus x of I has to be equal to x of I minus x of I minus 1. So we should say provided this is the case. If this is not the case, if the 2 points are not equally spaced, If the 2 points are not equally spaced, then we cannot use the central divide difference scheme. So that's one thing which we have to keep track of. So let's go and take an example and see how the three divide difference methods which we have learned, the forward divide difference method, the backward divide difference method, and the central divide difference method for finding the value of the first derivative, approximate value of course. And we're going to see that, hey, which estimate is the most accurate. We'll have to determine that. So the first procedure we're going to talk about is forward divide difference method. So if we want to find the value of the velocity at 1.75, that implies that, hey, do we have a data point available ahead of it, which it is true because we have a data point available at 2.51. So in that case, the velocity at 1.75 will be equal to whatever is the location at 2.51 minus the location at 1.75 divided by the differences of these two times, which is 2.51 minus 1.75. So based on that, what we'll be able to do is we just simply substitute the values. We get 274 minus 262. And that turns out to be 15.789 meters per second. So that is the approximation which we get by using the forward divide difference method. Let's go and see what happens when we use backward divide difference method. So we have the same data, the problem statement is the same. So if we have the backward divide difference method, now what we have to see is that, hey, we are trying to find the velocity at 1.75 seconds. Is there a point available before it? Yes, we have 0.99 available, which is the closest point to 1.75 behind it. So in this case, the velocity at 1.75 would be approximately equal to whatever is the location at 1.75 minus whatever is the location at 0.99. We divided by 262 minus 211. No, we divided by 1.75 minus 0.99. So in this case, we have the value at x at 1.75 is 262. The value at x at 0.99 is 211. And this number here turns out to be 67.10 meter per second. So that is the backward divide difference method we get. Let's see what we get by using the central divide difference scheme. So in the central divide difference scheme, now what we have to think about is that, hey, we are trying to find the velocity at 1.75 seconds. So we got to have a point behind and we got to have a point front. So that is there. But we also have to make sure that the distance between these points is equidistant. So we have 0.99 here and 2.51 here on the time domain. The difference between these two times is 0.76. The difference between these two times is also 0.76. So we are good there. So we can apply the central divide difference scheme, in which case the velocity at 1.75 will be approximately equal to the value of the velocity at 2.51 minus the velocity at 0.99 divided by 2.51 minus 0.99. So here we get 274 minus 211 divided by 2.51 minus 0.99. So that is 63 divided by this quantity right here, and we get 41.44 meters per second. So if you look at the three values which we have got from first from the forward divide difference scheme, for the velocity and the backward divide difference and the central divide difference. I'm just going to write those down. We got 15.789. We got 67.10 meters per second here. And we got 41.44 meters per second here. So what you're basically seeing here is that this is the order of accuracy of h, the step size. This is order of the accuracy of the step size again. However, this particular value is order of the accuracy of the square of the step size proportional to it. So what we know is that that the central divide difference scheme answer which we have here is the most accurate out of the three which we obtained by using our divided difference scheme. And that is the end of this segment.